For our physics project, we demonstrated that a change in moment of inertia on a rotating body will change the angular velocity. We first measured the radius of the merry-go-round by figuring it was about half the height of Abby, and since Abby's about 5'6", we figured it would be half of that. Next, Aiden applied a torque to the wheel. So after Aiden applies a torque to the wheel, Rav and Abby are moving at a certain angular velocity. Once they go to the middle, the moment of inertia decreases because the radius decreases, therefore increasing the angular velocity. And that is because the angular momentum is conserved. And as you can see, when they go back out to the outside, the moment of inertia is increased again, which decreases the angular velocity since the angular momentum is always conserved. Now we had Aiden do our calculations and explain how we got our answers.
So a carousel in itself is a torque-free environment because the bearing that it is rotating on means that while it is rotating, there are no outside torques acting on it. So that means that its initial momentum is equal to its final momentum. And so if we were to try to find the final angular velocity of the carousel once two people moved closer together, sitting on the carousel, then we first need to find the initial angular momentum. And so we were able to do that by finding the initial moment of inertia and the initial angular velocity. So the initial moment of inertia is calculated by the moment of inertia of the merry-go-round, which is essentially a disk, so that means the moment of inertia is essentially 1/2 mr squared. And then we add 2 point masses of the two people sitting on the carousel. So we have the mass of Abby times the radius of Abby squared plus the mass of Ravneet plus the radius of Ravneet squared. And then in order to calculate the angular velocity, we then looked at the footage and determined how fast the merry-go-round was rotating. And we determined that every 4.06 seconds, the carousel completed 1 revolution. And through dimensional analysis, we converted this to radians per second, and we got that the initial angular velocity is 1.55 radians per second. Our initial moment of inertia we calculated was, from this equation right here, we calculated that it would be that, which then comes out to 112.9 kilogram meters squared. And so since L equals I omega, we then multiplied 112.9 kilogram meters squared by 1.55 radians per second in order to get an initial angular momentum of 175 about kilogram meters squared per second. And so, since it's a torque-free environment, that means that the total angular momentum of the system will never change. So that means that the initial angular momentum is equal to the final angular momentum. So that means that initial moment of inertia times the initial angular velocity will equal to final moment of inertia times the final angular velocity. So we have the initial angular momentum, that is 175 millimeters squared per second, and then we set that equal to the moment of inertia final times the angular velocity final. So the goal would be then to find the angular velocity final, and so we would first need to find the final moment of inertia, which we then calculated by looking at the radius of the two people after they had moved closer together on the carousel. And so we determined that they had moved about 0.3 meters closer to the center of the circle. So the radius decreased from 0.84 meters to 0.54 meters. And so plugging 0.54 into the radius in this equation, we get that the new moment of inertia was 63.2 kilogram meters squared, which is markedly smaller than 112.9 kilogram meters squared. And so in order to find the final angular velocity, we then divided the initial angular momentum, which is also the final angular momentum, so 175 kilogram meters squared per second. We divided that by the final moment of inertia in order to get our final angular velocity, which then we calculated as 2.77 radians per second, which, as you can see, means that as the two people moved closer together on the carousel, the angular velocity of the carousel increased in order to account for the decrease in moment of inertia.